sure to introduce our next speaker, Deepak. I'm not going to embarrass myself trying to pronounce his last name. Deepak is a senior engineer scientist at EPRI in the Grid Operation and Planning Group of the power delivery and utilization sector. Deepak joined EPRI in 2017, where his work is in the area of modeling, control, and stability analysis of the power system, with recent focus on the associated impacts of large-scale integration of converter interface generation. With that, I'll hand it to Deepak.
Thanks, Yashin. So thanks for having me here. Some of the topics that I'll be talking about today, hopefully they try to address some of the questions that we've been talking about already in the discussion session and just generally over the entire day. And it'll be split up into 3 different components. All of it is not necessarily grid forming, but they're all from the bulk power system point of view. They have all ties to grid forming in some way or the other. And it's from a perspective of what would we see from the bulk power system and not necessarily in the in-depth controls that may be there. Before we go further, I can't help myself but to address one of Eddie's questions that was raised before. Momentary cessation can be modeled with the inverter models that we have nowadays. We admit that there is limitations in modeling it, but it can be modeled. The only reason why we couldn't see it was because the models were not parameterized properly. Wrong parameterization of any model will give you wrong results. That does not necessarily mean that the model is bad, while there are limitations of the model. So we can parameterize, we can see it, we can get to see momentary cessation, we can see delay and recovery, we can see all of those things within certain rules. So going further from that, the background and the motivations for this talk is that predominantly when we look at from bulk power system, everything is positive sequence, right? So we use software like PSLF, PSSE. In Europe, there's Dixisland Power Factory, which has an RMS-based module, and everything is in that realm. So unless we go towards full EMT, which there's a lot of obstacles to going towards full EMT, we have to work with this positive sequence setup and see how much we can extract from it, what are the limitations of it, when should we not use it, and what else can we do with that. Going hand in hand with that is the concept of generic models. Now, unlike synchronous machines where there's a definite physical property or Newtonian dynamics associated with it, inverter-based controls, it's pretty much it's open game. So any inverter manufacturer can have their own controls inside the inverter, and it becomes essentially black box. Nobody can see inside it. But from a system perspective, in order to be able to assess, in order to be able to do future planning studies, in order to be able to do an interconnection-wide studies, generic models are used, which gives the general trend of what's happening to give a reasonable picture of what may happen with these inverter-based resources, coupled with the fact of recognizing that in reality, every inverter or converter is a voltage source. It may be controlled to be a current source, but in reality, it is a voltage source. And the current source interface only comes into play because of the current controls and the high bandwidth controls that are there, which are valid only under certain network topology assumptions. So keeping that in mind, we go with these generic models. And for those who are not familiar with the generic models that are there, actually, Abe Ellis is the proponent of all of these models. And they're called REGC. I mean, the generic names are with respect to their split and modular structures, with respect to what kind of functionality they portray or what component do they portray with respect to modeling these inverter-based resources for bulk power system analysis. So this is the basic module of what is REGCA, which is the state-of-the-art way of representing converter-based resources, at least to the interface to the network, in positive sequence simulations nowadays. This is the most ideal grid following controller representation that you can have. because the entire converter interface is modeled as a current source model with injections into the network. There's no representation of the fast dynamics of trying to capture the phase angle, no representation of trying to control current. There's nothing with respect to that. All the background slower controllers with respect to either frequency droop or voltage control is there behind this where the current commands come in. But in generality, this is the ideal grid following controller. And this model has been known to have limitations as we keep getting more inverter-based resources into the system. You can have numerical instability issues, which could probably one of the contributors why ELU couldn't get more than a certain penetration of inverters into a simulation, because this model, the way positive sequence simulations are run, you cannot solve the network equations when you have more and more of these models in the picture. You just run into so much of numerical convergence issues that you can't trust whether the output that you're getting out of the simulation is an actual instability or just the fact that you couldn't solve a numerical equation. The other thing is these models cannot represent some of the oscillatory behavior that we've been seeing. There have been numerous recordings which have been observed with respect to inverter-based resources in the system, depending upon the change in topology, depending upon the controller gains, you can have oscillatory instability. These models can't represent that because of the fact that they are true grid following current source models. So, and this is one of those limitations. So this is from simulation, this is replicative of measurements that we have seen with respect to the fact that what you see on the blue line is present day state-of-the-art bulk power system positive sequence models that are used. And for certain network topology conditions, you can ride through the fault. Once the fault clears, based upon how the post-fault network is represented, the positive sequence model would provide a stable response, whereas with different flavors of EMT models, whether you model the background dynamics of the source, whether you model the DC dynamics or not, or even taking the most restrictive or the most simplistic EMT model you can generate, you can still see those oscillatory instabilities. And if a system planner cannot see those stabilities, then that's a bad thing. So if the system planner cannot observe the fact that a certain network topology for a certain penetration level or for a certain megawatt level of resources, if they cannot see that instability that might occur, that can lead to wrong conclusions regarding the stability of the system, and it affects entire planning and operations. More generally, the reason why that instability occurs is going back to the fact that it's partly because of transmission line dynamics. It's partly because of the fact that you have fast current controllers, and if you have, and pretty much where this kind of instability occurs depends upon if you're connected to a weak impedance or a large impedance and a low short circuit scenario. In that large impedance with a fast controller, control theory 101, if you have a slow system or if you have a fast moving system, your controller has to either be faster than that fast moving system in order to control it, or you wait for certain dynamics to die down and then you control it. What happens here is in your representation of the controls in these oscillatory behavior which you're observing, fast inner current control loops and fast PLL controls are trying to track a fast moving system, and they are not able to track it significantly or sufficiently well. So that results in injecting current at the wrong phase into the network, and that causes this instability. This is not something which is new to inverter-based resources. This has been observed when you have hydro turbines connected to a very long transmission line and static excitation on those hydro turbines. So this is a problem which has been known from machine theory also. One of the ways to solve it from static exciters, put a rate feedback in the exciter. When you put a rate feedback into the excitation system, you slow down the excitation system in order to take care of the transients that might occur in the flux dynamics, and you can stabilize the system. It's a similar concept here, but now how does a transmission planner get to view this kind of an oscillatory instability? So we set about trying to modify one of, yes, Henry. For the fault cleared. So this is the duration of the fault. So the question is then, how can we get a transmission planner to try to get some of these, a visual on some of these oscillatory instabilities that might occur? So we've been working on one flavor of these improved positive sequence models. I have to say that this control diagram looks a little bit complicated, and it was even more challenging to try to draw it out properly. But with respect to the fact, essentially what it has is, it has representation of the phase lock loop, it has representation of the inner current controllers. It's not a pure representation of the phase lock loop because positive sequence simulations already run on a phasor-based domain or a phasor-based analysis, but it is a representation of those generic phase lock loop controls. And then you run it at a smaller time step. Not traditionally, positive sequence simulations are run at 4 milliseconds because that's quarter cycle. We run it at 1 millisecond to get this the representation of these dynamics. And in addition to that fact, we remove the interface, which would have been traditionally current source interfaces. We put a voltage source interface onto that. Putting a voltage source interface here doesn't necessarily mean we are completely saying this is grid forming or grid following. It's just a representation of the fact of how, when you would model a converter, when you have slower dynamics in the inner current control loop, which you have to slow down if your transmission line dynamics are fast, then you have to slow that down, and then you have to get representation of the fact that it is actually a DC source connected to the transmission system through switches. So we get representation of that through this, and because of that, you inherently get numerical stability also. And with that, we can represent some of these oscillatory behavior that occur from EMT simulations. So what's shown here is the same positive sequence scenario, or the same positive sequence simulation that the blue curve in this slide showed as a straight response. It's the exact same scenario, exact same system, taking some of the parameters of the EMT model in this case, parameterizing the positive sequence model appropriately. The parameters don't transfer one-to-one because it's two different kinds of modeling scenarios, but you can parameterize the model to show some of the same oscillatory instability scenarios. Now, of course, what we are saying here is that, or the disclaimer that has to be put here is that this doesn't mean that we can do away with EMT studies. EMT studies always have their value, they have their place. All that we're trying to do here is bridge the gap between EMT studies and positive sequence simulations such that a transmission planner can now start getting visibility on some of these instability phenomena that may happen from inverter-based resources connected at far out places in the system. And once you start getting visibility of that, you can start planning for it. There are many ways to mitigate this instability. It's with respect to the fact of either curtailing or retuning or anything like that. But if this instability can be identified in a generator interconnection process itself, then that itself is a very much a positive phenomena that a transmission planner can then use to further inform or further tell the GO, the generator owner, that these are things that need to be done to try to mitigate the instability. Can it also represent, so this is large signal stability. Can it also represent small signal stability? Yes. This model can represent some, we took a plant, a solar plant, which manifested small signal oscillations during real-time operation in the day. We worked with the solar plant vendor or the plant developer. We replaced this model with the models that they had, and we were able to replicate some of the small signal oscillations that were seen in measurements with this model, which the original positive sequence model couldn't replicate. So what this model is doing is it's taking some concepts with respect to the fast moving dynamics that are there in controllers, existing controllers, and putting that or showing that to a transmission planner so that during a planning phase, this can be identified. So now this comes, the next slide, Brian told me, can be a little bit outside the lines of what we have defined in our working roadmap document, but I'm just going to put it out there for discussion because this is something which we are looking for answers. Is this model a grid forming control? The way I look, or I wouldn't say model, is just this operational philosophy, not the instability. The instability can be, you can tune the controllers and get the instability, you can make it stable. But just from the perspective of what the grid is seeing, can this be a form of grid forming control? We like to think of it as possibly yes, for a couple of reasons. Firstly, every inverter is a DC voltage connected through switches. The switches have almost zero impedance. They connect, and the switches here are of course IGBT, so it depends upon how you're switching it. But at any point in time when each switch is in the on phase, any inverter is directly coupled through its filtered impedance to the grid. Which means that, and this is something that we have seen, so let's take this plot. What's happening here is the inverter controls were wanting to try to make the inverter run at unity power factor. What you see here, the blue is the reference command of the current. At unity power factor, you want zero current reference. The green is the actual current which comes out of this entire resource. In the subtransient time frame, because of the way this gets connected to the grid, and depending upon how robust this control is, there's nothing stopping the grid from pulling out current from the source. We can't violate Kirchhoff's law. So which means in the subtransient time frame, and now ultimately I admit that this kind of a response here need not be the norm. It completely depends from one inverter manufacturer to another inverter manufacturer, depending upon how robust their control is, depending upon how much control effort is put into the controller to try to force this current to be zero. But in the short time frame, there is a chance that the grid is viewing this entire resource as a voltage source. And if the grid is viewing the entire resource as a voltage source and there's loose control on the current, that's effectively what we've all been defining as grid forming. From a functionality perspective, let's leave the fact of whether it has a PLL or it doesn't have a PLL. From a functionality perspective of what the grid sees and what the grid needs, this is grid forming. Yes, sir.
But doesn't this depend on the inductor if it's a big one?
So this is the filter inductor of the inverter anyway. Now, yes, there can be other inductance here after the grid, which can be big depending upon the line impedances. But what I'm getting to is that there can be system topologies, there can be system networks, there can be load levels where this can happen. So which means that it need not be a specific, it can be a specific operational mode of a generalized situation. And that's something as a system planner you need to take care of or we need to consider.
Additionally, you can program also, let's say, virtual impedance if you control it properly.
Yes.
And this would also change the problem.
Definitely. Definitely. All I'm getting at is this is not the only flavor of control. I'm trying to put the perspective that the way we have defined things or the way we may need to define what is grid forming, what is grid following, we might want to take a deeper look into that. That's because from a system planner perspective, all that the system planner may care about is functionality. If you don't mind, I will come to the questions after I finish. Otherwise, I might get pulled out for overshooting time. So, and then there's a whole different scheme of, okay, fine, you have this, what will we do about power sharing? So we had this angle group scheme, which is very much like what Marcelo was saying. It works on the principle of if you consider in a power flow scenario, when you solve a power flow equation, we usually have one slack bus. But you can have a distributed slack bus concept where you can change the P reference value of every generator or every source in the power flow based upon mismatches of angles. That mismatch of angle can be internally calculated and not necessarily with respect to a fixed reference. And that's the kind of control that we put in. We tested it on various systems. One of the and various cases. I'm not going to go into very much detail here, but suffice to say that we tested a scenario where we were looking at 80% inverters, right? So at least for this case study, where we still had around 11% with synchronous machines in the system. And then depending upon whether you have a PLL-based control or whether you have a pure voltage source, whether you have an ideal voltage source, whether you have droop control, whether you have an angle-based droop control, we took it to that perspective and we looked at what will happen if there is loss of generation. Now this is for a system which is said to be statistically equivalent to ERCOT. For those who are not familiar with ERCOT system, it's around 60 to 70 gigawatts of generation. The largest contingency, which is supposed to be tested for ERCOT, is a loss of 2.5 gigawatt of generation. That is the NERC recommended testing to see if there's adequate frequency response reserves. And we were looking at this case. This is not the actual ERCOT system, of course, but it's said to be statistically equivalent to it. And what we wanted to point through here is that as we start moving towards an all-inverter system scenario, what is frequency? We know of frequency. We all our notations, definitions, criteria with respect to how frequency should behave is governed by synchronous machine systems. Now, as the resource is changing in the system, do we want the system operational constraints to remain the same and make the individual resources cater to that operational constraint? Or can we go to an operational paradigm where we change the way the system itself operates and make use of the fact that the inverter-based resources can provide a much more superior control functionality and operate the system in that manner? So we were looking at it from that perspective, and what this ultimately boils down to here is, in a way, making every inverter-based resource have an isochronous governor, or a controller which is mimicking an isochronous governor. But firstly, to get rid of the main drawback of an isochronous governor, where in an isochronous governor, we don't have isochronous governors on synchronous machines because each of them are going to be trying to maintain a slightly different value of speed, and they might fight against each other. So to do away with that kind of a drawback, we implemented the angle group control, wherein depending upon each inverter control, it's tracking its own angle, looking at how its own angle is deviating from a predefined reference. That reference also is calculated by itself internally. It doesn't have to come from any system operator. So by looking at how that angle deviates from that predefined reference, mimicking what you would do in a distributed slack scenario for power flow solution, you can share power across the inverter-based resources. And then you can share power across areas also, as we want to do it in an interconnected system today. We've been looking at other forms of grid forming control with respect to the fact of either we purely take a look at remove the inner current control loops, remove the PLL, assume that you can either have instantaneous measurement of the phase angle, or you have an oscillator clock inside which is giving you the instantaneous measurement of phase angle or frequency, if you'd like to call it, and just look at the external controls and see how the system would behave, how a large system would behave. We've been looking at what would be the impact of putting inverter-based inner current control loops to have that adequate control of current, because if you don't have that control on current, there could be situations where, because it's the pure voltage source, the grid takes how much of current it needs, and you could violate the current ratings of the devices. So how to put in a form of current control into the fact that when you don't have, or when you have an oscillator clock behind the inverter, so you have that form of voltage source control, but with a current limited control, so that when it hits the current limit, it stays at the current limit, and can we still keep the system stable? This was tested on the WEC system by essentially looking at 100% inverters. Of course, when we looked at 100% inverters here, we assumed that the same amount of reserve headroom which was there on the machines remains on these inverters, and we were not trying to play around with the reserves, because we like to think of the fact that if we do go to that level of a system, as we were having in the discussion, we would still like to try to be able to ride through loss of the largest disturbance that we have. And given it's highly likely that that loss of that largest disturbance may be a different value in an all-inverter system, but looking at the present planning that we, or the present way we plan our systems, we kept the same value of megawatt of loss to look at what will happen. This is just looking at different sensitivity studies. I'm not going to go into this in detail. And again, looking at if you have load response, if you have only a particular amount of resources providing this frequency response based upon geography, looking at if they have different forms of control on them, what will be the trend and response of a large system. We have other types of controls that we have devised. All of these controls have been developed for use in a positive sequence scenario for studying a large system, but validated based upon detailed EMT scenarios. So one of the things that you see on the top left is just the ideal unlimited current grid forming converter. Essentially, it's an oscillator controlling voltage magnitude, and it's not going to try to control current at all. And we have another way where we have what we call a control grid forming topology, where again, it's going to try to, the voltage source interface still remains and you still have an oscillator inside, but then you can now do some form of voltage control and some form of frequency group control externally to try to move the system to where it needs to be. The third kind of thing that we've looked at is looking at what role will, if you have a source behind the inverter, traditionally in all our simulations for bulk power systems, we assume that the source behind the inverter and the DC bus dynamics, we don't need to really look at that for the time being because they're either fast or they're stiff enough that it doesn't play a role in large system dynamics. But we've started looking at what if you put, say, a wind turbine or a type 4 wind turbine behind a rectifier and you have the DC bus dynamics of that capacitor on the DC bus, what role will that dynamics play? Can you model that? Can that model be used for large system studies? Is it computationally tractable? Does it give results in a form of which is viable, which is justifiable and verifiable? So from a bulk power system point of view, this is something which I just have to open up to questions, trying to redefine what we had in the roadmap document. Firstly, we're not looking at black start. So when we talk about grid forming, when we talk about all of that, we're not looking at black start capability for the specific reason that even today, not all synchronous machine plants are required to provide black start. There are specific services they are required to provide. And if they are required to provide black start, they have specific controls on them. So we don't want to equate the fact that, okay, you can have grid forming control and can provide black start, but that is a subset of what you might need from a system point of view. Every inverter-based resource, irrespective of whether you have grid forming, grid following, PLL, no PLL, will be current limited. The limit on the absolute value of current injected from a converter is not dependent upon the control, it's dependent upon the rating of the switches. So that has to be kept in mind and that has to be considered while we define these things. And every control has its region of stability limits. So if we take that into consideration, then the question that I ask is, should we define grid forming converters as anything which does not have a PLL? And why I think that's a little bit restrictive is because then by default, it means that if grid forming controls are mandated or required, it means that no PLL will be allowed. And the way I like to look at it, it's like telling a synchronous machine that you cannot have a static exciter, you have to have a DC exciter. And that is something which we don't mandate nowadays. It's completely left to the OEM, the original equipment manufacturer, to decide what is best for their equipment, what kind of control is good for them, as long as the system planner can define or can require robust, stable, and grid-friendly control. And if that can be specified and can be required, then I'd like to just put this thing of our inner Shakespeare from Hamlet. To be PLL or not be PLL is the question. So what can we do from a grid forming perspective? What can we do from a system perspective about that? Now, I know we're coming up. I have a couple of more slides which I'll run through very fast. I see the time there. Looking at from distribution system perspective, we like to look at block tripping, or we wouldn't like to look at. We have to look at block tripping because it's a very crucial component that can occur. And we've been doing some work with respect to the DERA model. Some of you are familiar from the roadmap document. I'd just like to put a point out there that the DERA model is meant to represent an aggregation of distributed energy devices on the distribution system for the transmission system. It's not meant to represent one particular device. And because it's not meant to represent one particular inverter device, it doesn't have representation of the source dynamics. It's meant to represent an aggregation of devices. And we've been doing work, I'll be happy to talk about it offline, about how to parameterize the model, how to get a system planner to view some of these tripping events that can occur. And finally, from the protection implications, what will be the impact on existing protection settings when you have a lot of inverter-based resources? This set of slides is not from the fact of whether negative sequence current is injected or not. There are requirements which can inject negative sequence currents. This is more from the fact of whether power swing blocking and distance protection will misoperate or will they operate as these inverter-based resources come into the picture. Because as you have more and more inverter-based resources coming in, the speed of your power swing becomes faster, and the power swing blocking may not be able to distinguish between what is a fault and what is an out of step. order to prevent or to allow or prevent the relay from operating. So we've been looking at some of those concepts also to see how do we improve the better state of the art of modeling? What do we need to do to be able to tackle this fact of how can we see these kind of behavior before it actually occurs? And I'll just leave it at this slide and questions. This is the final slide anyway.
Thank you, Deepak. Maybe one quick question.
I think there were a few questions before, during the presentation itself. So I'd like to give.
One question. Sorry, it's more of, let's say, first of all, support what you're saying, but then also maybe taking it further that that we have drawn a very narrow bit, like oh, it's with following it as a PLL, it's with forming, if it's like group control or something like this, which basically gives you all the services you would need. It's islanded, supports voltage frequency. And basically what you've shown here is that there are many things in between. So I would actually suggest you just ditch the notion of with forming and with following, because clearly we cannot divide these things just into and come up with a better terminology.
My way of looking at it is this. And I don't know if this is correct. All I'm saying is, if I'm looking at it from a bulk power system point of view, I have many sources connecting to my network. My assumption is that the requirement from each of those sources will be stable, be robust, be grid friendly. Do it however you want.
So you see the one that you showed and you said, oh, this is like grid forming. If you island it, it would not work. So very clearly kind of, you cannot just divide this into two things like this.
This is, so I'm sorry, this is for bulk power system stability. In bulk power system connected devices, if a wind turbine islands from the network, frankly speaking, and I may be wrong here, how that wind turbine operates in isolation when it has islanded from the network, a system planner doesn't care about it. So islanded operation, yes, there are some concerns regarding that. From a system, bulk power system point of view, everything is grid connected and how things operate when the grid is running. It comes down to the question the gentleman raised. It's all individual components playing with each other and being friendly with each other.
All I'm saying is that in large part of
Okay, in the interest of time, let's save the discussion offline. And let's thank Deepak again.